only the laws of probability. And of course there is, okay, I could call this H3, but this is not an essential hypothesis. As I said, you can just use the bounds, get the supremum of all these values and continue the same way. But it just simplifies if we don't. So let's find, okay. So this is true for any model that obeys this hypothesis. So the next question is, does quantum mechanics obey this model? Right? Is this true for quantum mechanics? So we need to know, we need to find a set of operators in quantum mechanics that obey this. And you know that. That's just Pauli matrices. The Pauli matrices are exactly like this. So we can use the Pauli matrices and see what quantum mechanics tells us about the same combination of expected values. Okay, so let's do that. So that, okay, so this is, there's a leap here, so this is true from a, so to speak, classical model. So let's now let's perform the same calculation using quantum mechanics. So the question is, this quantum respect Rosenholm presumably holds inequality. So let's see. So take A will be A dotted with sigma. To avoid confusion, again, I don't really need to label, but I'm going to put a label just to make it abundantly clear. Just to say that this sigma doesn't have to be the same for the other one. So these operators A and B satisfy these conditions. So they can only assume +1 and -1. Why? Because how do you know that it's true? Well, just take choose your coordinates. So A is parallel to the to one of the axes. So this is just one Pauli matrices, and the eigenvalues of the Pauli matrices are +1 and -1. So this does the job. Now let's choose a combination of settings. We have A prime, B and B prime. So let's choose the following combination of settings. Why? Because this works. This will do what we want it to do. So let's choose this combination of settings. So here I have my diagram. So let me put the z-axis on top and the x. So they're all going to lie A prime, B, and B prime, all going to lie in this x, z plane. So let's start. Let's take A parallel to Z. That's my A. B is going to be rotated like so. 5/4 rotated counterclockwise. A prime will be -x. And B prime is going to rotate the other direction in respect to A. Right? So let's be precise. So this is for us to see, but let's write this in terms of vectors. So A is going to be the unit vector in the z direction. A prime -x, as you can see from the picture. B is going to be root of 2 divided by 2, z minus x. Yeah, it's positive in that, in the vertical, and negative there. And B prime is going to be negative in the other direction. So, well, I think this is incorrect. We have a minus sign, but it is. So why do I have a minus sign? Oh, I'm saying that this is rotated here. Oh dear, did I use this convention or this convention? Give me 1 second. Let me see which convention I used. I found Contradiction in my own notes. Which convention did I use? So, I got the one that has a minus sign, Z prime, B prime. Yeah, I think I chose this one. So I chose it with plus plus. I chose this one. So trust the feeling. Anyway, okay. And let's take a stage. So this is in our stage. This is going to be a spin singlet. So 1/2 1 square root of 2 of plus, minus, 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 plus. So that's just the B3 Bell stage. Okay, right. Now let's calculate one of these expected values in quantum mechanics. So let's find, we need to find something like this. So let's find psi A dotted sigma A O times B sigma B. Well, that's not difficult. By this stage, you're experts in calculating these expectation values, but let's do them together. So this is 1/2, y 1/2, 2, I'm taking the bra and the cat, roots of 2. So 1/2, we have got down, up, down, and 1. Well, this is just writing generically because I'm going to have to do it 4 times. So let me leave the angles generically. So that's why I'm not writing A, writing N, just so we can change the angles as we need them. O times N2 sigma up down minus up, down, so now up, down, and down, up. Down, up, with a minus sign, plus, well, let me give him some room. Well, another minus. Let me give it some room here, another minus. Now it is down, up, up, down, and then plus, minus, and minus are plus. So now down, up, down, up. Okay. So what is this? Now I have to calculate one by one. So this is eigenstate of the z direction, right? So these ups and downs are the eigenstate of the third Pauli matrix. So n1, so this is just the expectation value of n1 times n1. So this is just the product of the expectation values between this and this one. Right? So these are just minus, so this one is minus cosine of theta 1 times minus cosine of theta 2. Theta is the angle with the z direction. This one, well, okay, well, let's do one of them. Let's just, to make it exceedingly clear. So for example, this one is something like up. So up we can write it as 1, 0. Then n1 dotted with sigma. So n1 dotted with sigma, what is, okay, what is, okay, so let's make it super explicit. So what is n1 dotted with sigma? Well, that is just the same as cosine of theta times sigma z, which is 1 minus 1, plus sine theta sigma x, which is 0, 1, 1, 0. So this is just cosine theta, sine theta, sine theta, minus cosine theta. So then we can do, so what I did for this one, for example, so, well, we can choose one, right? So this one, we'll pick this, so this n1 sigma acting on this down is going to pick a sine of theta, right? Because then it, well, then it's something like up n1 sigma up will be 1, 0 times this matrix. Times itself, right? So this is going to pick up minus cosine of theta. That's what I wrote here, right? And same for the other one. So this is going to pick up minus cosine theta too. Now this one is up with down. So this one has 0, 1, 0 on top, and 1 on the bottom. So this one is going to pick up cosine, sine of theta. Times 1. So this is one going to pick up sine of theta 1. Now this one is down with up, so this one is also going to pick up a sine theta 2. Because it's down and up. So just like the other. Okay. What about this one? This one gets a down and an up, so it gets a sine of theta 1, and then it gets an up and a down, so it gets sine of theta 2 again. What about this one? Well, this one gets down and down, so this gets minus cosine of theta 1. And then it gets up and down, so plus sine of theta 2. No. Plus, plus. Up, up. No, this is no sine. This is cosine. Okay, so let's sum all this. So this is, oh, there's a minus here as well. So this term is the same as this term is the same as this term, and I have 1/2, so I remove this as 1/2 from the game. I get minus cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. But this is nothing but minus cosine theta 1 minus theta 2 minus theta 1, or theta 1 minus theta 2. Cosine of x is the same as cosine of minus x. Okay, very nice. So for this state, and this choice, for this state, And for this choice of A and B, this whole object is just the cos minus the cosine of the difference of the angles, or the angles between them. So forget about the z-axis. You just measure the angles between them. Right? So now we're going to have 4 of these expectation values that we just calculated. But now we don't have to repeat the calculation, because all we have to find is the angles between every pair here. Right? So let's see what the left-hand side is. Well, may erase this calculation of this matrix element. So let's see what the left-hand side of the analog of the Clausen-Horn-Shimony-Holt, what that will be, just so I don't have to write everything. Well, between A and B, the angle is 5/4. Cosine 5/4 with a minus in front. Between now A and B prime. A and B prime is also minus 5/4, which is the same as cosine of 5/4. So we have 2 of these. Plus A prime and B. A prime and B is also 5/4, so I have 3 of those. Plus, or minus, the A prime and B prime. A prime and B prime is cosine of 3/4. Close to 5. So what is this?
Question.
Yeah.
Should the negative not cancel out with cosines? Or are those not supposed to be negative?
This?
No, like up with your original terms. Because you got negative cosine theta 1 times negative cosine theta 2. Won't that just make it positive cosine 1 theta 1 cosine theta 2? I think it is. I think you are right, because of the fact that it should be up down, and it's going to be positive cosine times negative cosine.
Sine minus cosine.
And so
And
you
then
yeah.
the first one is up
should be
and
positive,
up.
right?
So this gets 1, 0, so it gets plus cosine and 0. And yeah, so this
yeah,
is
so that's plus, and the second
and
one
if
is
this one is
the second one will be minus
minus,
plus.
yeah, this second one is minus, so this is plus. Thank you. Thank you.
Why shouldn't it be negative cosine theta 1 positive cosine theta 2 in that case? Because of the fact that it's down up for the second one?
Ah, yes. Yes.
Okay, but then that will affect your final answer. No, it won't. No, it won't. Never mind.
Yeah.
You just
So, okay, that was, so this is a mistake. So in my notes, okay, let me, I haven't uploaded the notes for this part yet, so I'm gonna fix the sign. Yeah, thank you.
I mean, it works out the same.
No, thank you, thank you, thank you. No, that will be anticlimactic if we got the wrong prediction here. All right, what is this then? What's cosine of 5/4? Root 2 divided by 2. And cosine of 5/4 is minus that.
Yeah.
So this is, oh, this is a plus because of this minus here. So this is minus 2 root 2. Quantum mechanics does not obey CH, DCH, SH inequality. That was Jones Bell's realization. Well, Jones Bell's inequality was, well, this is a particular case of his inequality. So it's clear, quantum mechanics cannot be explained by this local H1 hidden variables that is encoded in H1 if we don't believe in superdeterminism, which was H2. Now, obviously, what does nature obey? If nature is what like quantum mechanics predicts, I can perform the experiment and obtain a violation of, well, I can obtain -2√2, or it can obtain a value bounded by -2, larger than -2. Well, the experiments are completely unambiguous. Quantum mechanics is right. There is absolutely no ambiguity in the interpretations. The experiments were repeated in different settings and in different labs, and there's just no room for dispute. Nature agrees with quantum mechanics. And that was the Nobel Prize for Physics in 2022. Any questions? Did you follow the derivation? You see that it's not a difficult derivation. But it, of course, it requires ingenuity, because you had to think of this particular combination. And I think I gave a public talk about this in the library last year. I didn't prove it the way I did, but I made a tiny table and I calculated this from the table. And someone asked, how did you know you had to put a minus sign? Well, I didn't know. It worked. With the minus sign, it worked. Yeah.
So is that always going to come out and be negative? Or is there any case where it obeys the CH?
No, for certain states, they will obey.
Okay.
For example, this is an entangled state. It's also true if you had a plus sign, but you have to choose different angles. But they also, so these are an entangled pair. So if you don't have an entangled pair, they will obey closing parsimony mode. So this has to be, they have to be having entangled. Yeah.
Is N2 just equal to N1 in this case?
No, the one has an angle of θ1 with the z-axis, and the other has θ2.
Okay.
And the key is,
I see.
So you see that the key here is that you have to have an entanglement and non-commutativity.
N is equal to cosine